truth tables. These are three tables that actually fully represent the three operators, not, and or. Let's take a look at those tables and try to understand their meaning. Let's begin with the first one, the not table, which is pretty simple. We can see in the darker color here the input, and in the other color, in the second row, the output. So for input 0, we get output 1. For input 1, we get output 0. The and or tables are a bit different. They look different because and or, they don't have only one input, they have two inputs. I remind you that not is an unary operator, however and or are binary operators. So we can see that and has two inputs. The first input is chosen here on the upper row, and the second input is chosen on the first column. Of course you can reverse it. Maybe you want this one to be the first argument and this one to be the second argument. And let's look at the results. 0 and 0 equals 0. 0 and 1 equals 0. 1 and 0 equals 0. And finally, 1 and 1 equals 1. Let's look at the OR table. Just like the AND table, the argument part, which is on the darker side, looks exactly the same. Only the results differ. We can see that 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, and 1 or 1 also equals 1. Some things to note about the tables. We can see that AND only results in 1 if both of the arguments equal 1, and OR only results in 0 if both of the arguments equal 0, which is kind of dual in a sense. If we flip all the bits, we can get a pretty similar result. This is just for thought. It doesn't mean anything very serious at this point. Another thing to note is the symmetry. We can see that we could take these four cells, 0, 0, 0, 1, and flip it, which has the meaning of changing the order of the argument. And we are going to get the same rectangle, the same 4 bits. The same goes for OR. We can take those 4 cells and flip them. It has the meaning of flipping the arguments, the order of the arguments. And we get the same 4 cells. By flipping, I mean flipping it around the main diagonal, this diagonal. We can see symmetry with respect to this diagonal, the main diagonal. The same goes for the AND truth table. Later we are going to see a bit of a different truth table, because sometimes if we want to have more than 2 arguments, we can't have it nicely like this, because our paper, or maybe in your case your computer screen, is only 2-dimensional. So if we wanted to add another argument, it won't fit in this 2-dimensional page. If we want to have 3 arguments, we will represent the table a bit differently. We are going to see this in the future. Some other representation is Venn diagrams. Venn is the name of the person who invented those diagrams. Take a few seconds to look at the diagrams and try to understand how do they relate to the NOT, AND, and OR operators. Let's begin with the NOT operator. I want to explain you what the diagram means. We have a circle, and the circle is inside this rectangle. This circle represents one argument. Every circle that you see here represents an argument. That's why the AND and the OR Venn diagrams have two circles, because they are binary operators, and so they have two arguments. The NOT operator has only one argument. Therefore, it has only one circle. Now, I assume that inside the circle means that the argument equals 1, and outside the circle means that the argument equals 0. And you might wonder, what is this color, this brown color? This brown color means a result of 1. And the white color means a result of 0. Now let's translate it to the actual table of NOT. If we have input of 0, we get 1. Therefore, the 0 part, which is outside the circle, is colored with brown, which is 1. I remind you that the outside of the circle means the input of 0, and we colored it with brown because 0 goes to 1 in the NOT table. Now let's look at the 1 input. 1 means the inside of the circle. The input 1 is represented by the inside of the circle. And because 1 goes to 0, we colored the inside of the circle in white color, because white means 0. I want to repeat it again. We have two kinds of symbolic ideas in this diagram, which are the inside and outside of the circle, and also the color. The inside and outside of the circle determine the input of the NOT operator. The colors mean the output. For input 1, which is the inside of the circle, we get 0, which is white color. For input 0, which is the outside of the circle, we get 1, which is brown color. Let's move further to the AND operator. If you haven't fully got it yet, don't worry. I assure you that by the AND and OR operators, you are going to understand it. Let's take a look at the AND operator. This time we have two different arguments. Each argument is represented by a circle. Even before we can see any color, we can see that there are 4 different types of regions in this painting. There is this region, which is inside both of the circles. There is this region, which is only in one of the circles, but not in the other one. There is this third region, which is inside the other circle, but not in the first circle. And then there is the fourth region, which is not inside any of the circles. This is interesting because also the AND operator has only 4 possible inputs. It could be maybe 0, 0, 0, 1, 1, 0, or 1, 1, which is exactly the 4 different regions that we have here. Now let's try to understand what we see in the picture. We can see that for AND, 0 and 0 return 0. How is the input of 0 and 0 represented in the Venn diagram? It is exactly the region outside both of the circles. And indeed it is colored by the white color, which means that 0 leads to 0. The color of the external region here, the white color, corresponds to this cell in the truth table. The cell here that contains 0. Let's talk about this cell, which comes from the input of 0 and 1. This kind of input is represented in this Venn diagram, for example, by this region. This region which is inside one circle but not inside the other one. And we can see that it is colored in the white color. It is colored in the white color because the output is 0. We also have this cell which is symmetric to this one. And in the picture it is represented maybe, for example, by this region. You can see that also in the picture we have this kind of symmetry. This region is symmetric to this region, and both of them are white. Finally, we have this special region, which is colored by brown. This region corresponds to the input of 1 and 1. Why is that? Because everything inside this region is inside both of the circles. The input of 1, 1 is represented by the region which is common to both of the circle, which is inside both of the circle. That's why this region is colored by brown, to represent that the input of 1 and 1 goes to 1, because brown represents 1 in those Venn diagrams. Finally, let's look at the OR table. We have basically the same picture like in the AND case. The basic picture, the outline of the picture without the colors, is mostly determined by the number of arguments. This picture, this basic picture, which is just like this one, corresponds to an operator with 2 arguments. Let's try to explain what we see in the last diagram, the last Venn diagram. First, let's begin with the outer region, which is colored by white. I remind you that the outer region corresponds to the input of 0, 0. Why is that? Because it is outside both of the circles. I remind you that every circle represents 1 argument, so outside the circle means that the argument gets 0, and inside the circle means that the argument gets the value of 1. So the outer region corresponds to the input of 0, 0. The outer region is actually corresponding to this cell in the table. As it results with 0, it is colored by the white color. Now let's look at this region, for example, which is inside one of the circles, but not in the other one. This region is colored by brown. We also know that this region represents input of 1 and 0. Why is that? Because it is inside one of the circles, but not inside the other one. We have here that both the inputs of 1, 0, which is this region, and 0, 1, which is this region, are mapped to the value 1, because both of these regions, this one and this one, are colored by brown. Finally, we have the last region, the inner region, which is also colored by brown, and I remind you that this region, which is inside both of the circles, represents the input of 1, 1. I also remind you that it corresponds to this cell in the table, the cell here that contains 1. So it is not surprising that this region is colored by brown too. Some other things that we can see in correspondence between the truth tables and the Venn diagrams. We can see that here we have 2 different outputs, 0 or 1. In the Venn diagram, the corresponding Venn diagram of the NOT operator, we can actually see exactly 2 regions, each one with a different color. If we move on to the AND operator, we can see that there are 4 different kinds of inputs, but only 2 different possible outputs. In the Venn diagram, we can see that we have 4 regions, which are colored each one by one of 2 colors. So there are 4 regions, and each region is either colored by white or brown. And here we can see that only one region is colored by brown, because only one of the outputs gets the result of 1. In the OR operator, we also have that there are 4 different inputs, and there are only 2 possible outputs, 0 or 1, which correspond to the white color and the brown color in the Venn diagram. This time there are 3 outputs of 1, which corresponds to these 3 regions which are colored by brown, against one region which is colored by white, which corresponds to this cell in the table. Some calculation examples. 1 and 0 is 0. If we negate the previous expression, we get the negation of 1 and 0, which equals the negation of 0, which is 1. We can also try something like this, 1 and 0. We put it inside those brackets, or 0. And because this part equals 0, and also this part is 0, we get that it equals 0 or 0, which is 0. Finally, we can even get a more complicated expression by negating the previous one, and we are going to get the result of 1, because the negation of 0 is 1. Some words about operators. We can create new operators ourselves if we wanted, by creating expressions like this. We have only seen so far 3 operators, the NOT operator, the AND operator, and the OR operator. We could now create our own operators using the operators that we know. We can, for example, define this new operator, F, which gets the arguments A and B, and results in A and the negation of B. Or maybe this operator, G, which has 3 arguments, A, B, and C. We haven't seen any operator of this type, which has 3 arguments so far. But now we can see one. And it results in A and B, or A and C. I want to look at an example of a truth table for this operator, for F. We can see here those 2 arguments, A, B, and the result, FAB. Here we list all the possible inputs. It is not so hard to do. We can just count from 0 to the largest number, which is 3. Okay, this is binary count. If you consider 0, 0 to be a number, we can increase it by 1 and get the next one, and then get the next one, which is 10, and then 11. If you try to put 0 and 0 inside this expression, you are going to get 0, because 0 and 1 equals 0. Now we try 0 and 1. 0 and the negation of 1 equals 0 too. We move on to A equals 1 and B equals 0, which gives us 1 and the negation of 0, which is 1. The last possibility is A equals 1 and B equals 1, which gives inside the F expression 1 and the negation of 1, which is 1 and 0. It results in 0, and we have 0 here. This was just an example of calculating the different outputs for possible inputs for this operator, the F operator.